Test. That's okay. Actually, I've been using this one. That's fine. Yeah. But I can hear you from a miles away. Okay, good morning. Let's get started. Let's continue on second order ODE. So today we're going to talk about non-homogeneous second order ODE with constant coefficients. Okay? In the last couple lectures, we did homogeneous second order ODE with constant coefficients. So now let's deal with non-homogeneous one. So first of all, what does a non-homogeneous second order ODE look like? So we're talking about a very simple case here. So it's ODE with constant coefficients. Thank you. This is what a non-homogeneous looks like. Apparently, you can see the term on the right side is not a zero term. Okay, if this term is zero, right, then you get back to your homogeneous case. So this is what we're going to try to solve. Okay, if I have a non-homogeneous in this format, what is the proper solution, okay, or approach to get the solution? Okay. I'm going to see myself a little writing, so I'm going to define and so-called an operator. Right? So I'm going to define an operator. An operator, just use a symbol, represent the operator, then with a bracket, right? Then you put you can put any kind of things into the bracket. So this time the operator is defined as so a d squared dt squared plus b d over dt plus c. So here's a operator I'm define this operator as this temporarily. So this might look a little strange to you, but it's just an extended version of or extended form operator like d over dt. So it's a derivative. So now you have this type of operator. So basically, if I write ly, so basically you put something inside the bracket, or put a y inside the bracket, then you get exactly the left side of the expression. So that's the usage of this operator here. Okay, so basically this non-homogeneous second order ODE, okay, can be shortened as writing Ly equal to f of t. If I use this definition of operator, then my non-homogeneous second order with constant coefficient can be shortened into this writing. All right, so now remember we're going to try to get a solution, right, for this one here. So I'm going to introduce a theorem. So this theorem will guide us in terms of provide a general guideline. What will be the general solution for this differential equation? So we're looking for general solution of Ly equal to f of t. Here's the description of the theorem. If yh of t, so this is h, it's a subscript. If yh of t is the general solution to homogeneous equation, Ly equal to 0. That's the first part of the sentence. YH is the general solution. L of y equal to 0 basically means this term equal to 0. And that gives us back that homogeneous equation, right? So we have done it before, you know, we have approaches 3 different cases to get a general solution for the homogeneous one. So this time, okay, remember this YH now is defined as this general solution for the homogeneous equation, okay, or homogeneous ODE. And YP of t is a particular solution to Ly equal to f of t. This is another piece of information. So YP somehow is a particular solution to the non-homogeneous ODE we're looking for. So if you recall, what is a particular solution? It's basically, it's not general solution, right? It's just some kind of solution that fits into this equation, right? So basically, if you see this is a particular solution, then if you substitute YP into this equation, it should satisfy the equation. So that's why it's called a particular solution. All right, so if we have these two information, okay, so you have a homogeneous general solution, you have a particular solution, okay, then the general solution to Ly equal to f of t is what we're looking for. Then it is y of t equal to yp of t plus yh of t. That seems pretty simple. You just add the general solution and the particular solution, add them up, and you get the general solution for the non-homogeneous one. So that's the theorem that we are going to use to solve this particular kind of ODE. Any questions so far? As a matter of fact, this theorem, right? So remember, we're dealing with a simpler case. The coefficients here are constants. So the theorem we just wrote it down at here applies to not only constant coefficients ODE, but also non-constant ones. Okay, so if you have a time function over here, so this theorem also works. So we're going to see some examples later. Okay. So let's examine this theorem a little bit again here, right? Yeah. So first of all, if you recall this YH, this YH is so general solution to AY double prime plus BY prime plus CY equal to 0. Oh, actually, before I forgot, just maybe a little bit reminder. I updated the lecture notes, okay, for the last couple lecture notes a little bit. So basically, in my lecture, if you recall, yeah. So in my lecture, I used y double prime plus ay plus vy prime plus by equal to 0. Right. So in my lecture, I used this to teach you the different cases. But I guess in my handouts, I use this one here. Okay. So to be consistent, I updated my lecture notes just to be everywhere with the AY double prime plus BY prime plus CY equal to 0. It's the same thing, you know, just to be consistent. Okay. So if you have downloaded the lecture notes, you can download again just to update accordingly. Okay. All right, so get back to this. So YH is a general solution. Okay. Then we learned that YH is basically will be the form as C1 Y1 of T plus C2 Y2 of T. And Y1 and Y2 of T are two particular solutions, right? Really depends on the three different cases, depending on the values ABC. So bottom line is this one, it's done. Okay, so you have this. You don't need to. This is not new to us anymore. Of course, you will need to solve for YH, but you know how to solve for this YH now. The tricky one here is how to find this YP of T. This YP of T is a particular solution, right? So how can we find this YP of T? And also, if you want the proof of the theorem, okay, so this theorem here, okay, in the lecture notes, there is a not a very long proof, half page. So if you're interested, take a look at the lecture notes about the proof of this theorem. Okay. So the next part of the lecture, and maybe also the lecture after this one, we'll focus on how to find this particular solution. And this has something to do with the handout I give it to you, right, which is taken out from the lecture notes. So we're going to cover two different approaches, okay, to solve for this YP of T. So just rewrite here a little more. So this YP is a particular solution to AY double prime plus BY prime CY equal to F of T. Okay, so there are two different techniques. Okay, the first technique is called method of undetermined coefficient. method of undetermined coefficients. A second approach is called variation of parameters. We're going to learn two different approaches to solve for this YT. Today, we're going to look at the first one, method of undetermined coefficients. So this first method, there's a different name. If you don't want to remember this method, it's a little mouthful. It's also called lucky guess method. Guess it's actually not too lucky. You have to based on certain rules, but it's sort of a aligned with the direction of guessing. So what is the key idea here? What's the key idea of this so-called lucky guess approach? So here's the idea, right? So you, let's say my f of t, okay, is e to the power negative t. F of t technically can be any function, but for some problem, let's say, for example, right now f of t is e to the power sine, e to the power negative t, or more often sinusoidal. Okay, so f of t, if you recall, this is your system input. Okay, so this is your either a force or kind of whatever function or signal. This is the input to the system represented by the second order ODE. So you can give it a delta impulse signal, right, or sinusoidal signal. Okay. If input is this, right, so you're looking for the output y. So the lucky guess basically saying is, could be possible that so f of t is input and y of t is output. Okay. So the question basically is it possible that output takes similar form as the input? So that's the key idea. Is it possible the output looks similar as the input function? So if the input function is exponential decay or sinusoidal, then could be that the output could also be an exponential decay or a sinusoidal. Of course, it may not be exactly going to be a sine t or e to the power negative t. Okay? It may be, for example, if it's sinusoidal, then the output maybe becomes a different amplitude and with a different phase. Okay? But probably still keep that the same frequency. Right? So that's the key idea. Because you're looking for a particular solution, right? So I don't need a general one. So long as I can find one particular solution, then I can use it to construct the general solution. Okay, so here is the following are the detailed rules or steps we should follow for this method of undeterminate. Okay. But before we move ahead with the rules, so let me write down one more comment here. So essentially, this method of undetermined coefficients this method is quite very much based on the type of function f of t. Quite pretty much determined by what the function f of t looks like. Okay, so here are the steps. Step 1 is called basic rule. So you're guessing, right? So basic rule basically is look at this function f of t. Then you use the table. You use a table that I give it to you, which is this lecture. So this table here. Use this table. So here's your function f of t. What it possibly looks like. Use the table to make a educated guess, so instead of lucky guess, right? Based on this given function f of t. So if your f of t is in the format of k times e to the power alpha t, then you need to pick your particular solution fyp as c times e to the power alpha t. So don't delete or don't shorten any one of the format here. You need to write down the whole expression for yp based on the type of input function. Okay. So for example, c here is a constant. That's what we're going to find out. All the k's here are constant. The n and m constant. The n and m here again is a constant. Right. So that's rule number 1. It's called basic rule. So use a table. This table is in the lecture notes to write down yp of t. Okay. So let me give you an example here. F of t equal to a constant 5. Okay. Constant 5. Typically, you can this is actually 5 times unit step function. Okay, that's a constant. Basically, it's like a unit step input to the system. So what would be your choice of yp of t? It's actually not part. Is it part of this? Yeah. So what would be the yp according to this table? Pardon me? A, yes. So where the A come from? I think it can come from the second one here, right? So with n equal to 0, that's a constant here. So when n equal to 0, so you only keep one constant here, called it k naught, but you can certainly use any symbols as you want. Okay, so let's take a look at this one here. Let's say 4t squared. Maybe even 4t squared minus 1. It doesn't matter, right? So f of t is the quadratic function 4t squared minus 1. Then what will be the choice or you educated a guess for yp of t? Okay, so you go back to this table. Sorry here. So you look at the table here. This is definitely in a format like this. So 4t squared minus 1, not exactly, right? Looks like kt to ktn, but that minus 1 is naturally included basically inside this expression here, right? So in this case, as a matter of fact, you could use a sum rule, but it will come up next. So in this case, this is the category belong to here. So when you write down the yp of t, okay, you can just write it down like that with the same order, because this is the second order. So you write a quadratic function here, but you write a full one, right? Even though this one doesn't have a term bt, but you write the full quadratic function bat squared plus bt plus c to represent the format of this input. Another easy one. F of t equal to 3 times e to the power of 4t. Okay, so apparently that's the first row. So your output, your lucky guess should be, let's say, a e to the power of 4t. It's your choice to what a symbol you want to use for the character. That's fine. Okay. Yeah. Okay. That's the basic rule. Okay, so your input function takes a format that's listed in the table. Then here's your lucky guess, educated guess. However, not always, okay, the function, the basic rule will work. Okay? So we have the second rule is called the modification rule. So this modification rule, and you can bet on it. So you probably will be, most probably means definitely, you'll be tested during an exam, right? This modification rule is a little bit long to write, okay? But let me explain this. Also probably explain it through examples, okay? So essentially, if this yp of t, okay, this yp of t that you have picked from the basic rule, okay, from step 1, or basic rule, if this yp that you picked happen to be a solution of the homogeneous ODE, homogeneous is that a y double prime plus by prime plus cy equal to 0. Right, so remember how we solve for the homogeneous solution? You have to construct the characteristic equation first, then you solve for lambda, then you construct y1 and y2 based on the 2 lambdas, right? So there are 2 solutions. There are 2 solutions for the homogeneous ODE, 2 particular one. Then you construct the general using 2 particular C1 y1 plus C2 y2. Okay? So the question basically is, it's very possible that this yp of t that you pick from basic rule number 1 is actually, okay, or happens to be the same as the solution of this homogeneous one. Okay. Then we're going to have to apply the modification rule at here. Okay, so then we multiply t. Okay, we multiply t to yp of t. So for example, right? See this example here. Your input is a 3e to the power 4t. Okay? And you picked your yp as a e to the power 4t. Okay, yeah. And then you find out that the solution to this homogeneous one, for example, lambda 1 equal to 4, maybe lambda 2 equal to 5. Okay, yeah. So then your homogeneous solution is what? C1 y1 e to the power y1 c1 e to the power 4t. Well, this is y1, right? And y2 e to the power 5t. So these 2 here are the solution to the homogeneous equation. And this guy here, right? This guy here basically in the same format as your YP. And that's the case time to apply the modification rule. Then you need to multiply the YP with a T to make it different from this e to the power 4t. So your YP of T needs to be T, and there's A here, times 4t. That's how you apply this modification. I'll show you one more example next. Okay. And even a little bit more complicated. Okay, so this is a one case at here. So this e to the power 4t duplicates with this y1 at here. So think about another case. Okay. Think about another case. So what if for the homogeneous one, okay, and you end up with, let's say, lambda 1, 2 equal to 4. Okay. So you end up with lambda 1, 2 equal to 4. So which is case number 2. And remember that case number 2 is called, it's a repeated roots. The roots repeated twice. Okay. And if that's the case, then the two solutions is e to the power of 4t, and the other one is t times e to the power 4t, right? You remember that to construct the general solution, you get the y1, y2, then cy1 plus cy2. That's for the homogeneous one. So now, if I still under this case set here, f of t is 3e to the 4t. Then you use a table according to the basic rule. Your choice yp is a e to the 4. So your choice of yp, right, initially is a e to the power of 4t. Right? Initially, that's your choice from the basic rule. Okay. So you look at this case 2, you said, okay, definitely this e to the power 4t is duplicating this e to the power 4t. So according to the multiplication rule, and I need to multiply by t. Okay. So you did that. However, after you've done this, which you multiply the t to the e to the power 4t, and guess what? It's further duplicating the other y2, right? So there's one more duplication. Then what do you do next? You multiply another t. Now this is basically become your choice of yp of t. So you're applying the multiplication rule twice at here under this situation. So bottom line is that you can see the reason you're multiplying the t or multiply another t is to try to make this choice of yp to be what? To be different from the y1 and y2 from your homogeneous ODE. So that's the point. You wanted to make it different. Okay. So you might wonder why, right? So this reason gets back to the theorem that we listed here. So remember the theorem of a general solution for non-homogeneous is y of t equal to yp plus yh of t. Okay, that's your general theory. So let's just suppose your yh is c1 e to the power 4t and then c2t e to the power 4t. Let's suppose this is your yh. Okay. And then your initial choice yp is this. Okay. So if you don't do anything at all, okay, if you look at the current, you compare these two here. Would you call yp actually as a particular solution? You look at the yp. YP is actually what? It's actually a family member of this YH added here, right? It's really nothing special. It's covered by this YH. So that's not what we want. We want a YP to be a particular solution. It's not part of the family of the homogeneous solution, right? So that's why you multiply by T. Try to make it different from this. However, after you multiply by T, and there's also a constant here, and it's still family of a member of this, right? Because there's a T to the power 4T here. So that's why you multiply by another T, right? To make it different. Okay. You don't want the YP to be a family of this YH. So that's the bottom line. Okay. So that's the second modification rule, right? So let me show you an example formally, show you an example here. Okay, so let's say we have a second order ODE, non-homogeneous, okay, written down like this. 3e to the power 2t. So as the theorem says, you need to find YH, and then you need to find a YP, and then you add them up. So YH is the solution of homogeneous. So the step to find YH is you construct the characteristic equation first, which is based on the coefficient of the equation. Okay, and then you solve for lambda. You get the lambda equal to 2, lambda 2 equal to 4. Okay, and you can easily separate into two factors, right? Okay, so you got two lambdas here. So that basically means your YH, right, equal to C1Y1 plus C2Y2, which is C1 e to the power 2t, C2 e to the power 4t. Right, that's your YH, and you're done. So now next step is to look for YP. To get the YP, you follow the rule. Okay, first step, basic rule. So you look at the form of this input function, which is 3 times e to the power 2t. And then you look at the table. Okay, so then I need my YP is 3 and not 3, a e to the power 2t, right, from basic rule. Don't stop here, right? As a comprehensive exercise, you always go to the second rule, modification rule, see if you need to apply or not. So you go to the modification rule. Modification rule, you examine your YP with any one of these Y1 and Y2. See if they duplicate. So apparently here, this one duplicate with this. Then you need to multiply, then you need to apply the modification rule, which is AT to T, right? This is multiplication rule, a modification rule. You need to apply the modification rule again, right? So you look at this, compare with the Y2, or you don't need to, right? So then you can stop here. So that's the process, right? A very, very common mistakes. A lot of students, they do not check, okay, or they just didn't notice the similarities between the YP and the solution for YH. So this is very important, okay? If there's test question, that this is very possibly will be part one of the kind of testing question. So I'm I will come back to this, how do we get this constant A value. Okay, but for now, right, that pretty much the first step to construct the YP properly based on the differential equation and also based on the form of the input function f of t. That's the second rule. Okay, so rule number 3 is called sum rule. And this rule is relatively easier to use. So basically, if the function f of t is a sum of functions, in the first column of the table, so then you choose YP, okay? By summing up from column 2, from second column. So I'll show you one example how you use this so-called sum rules and here. Let's say Fy of t, okay, is equal to t squared plus 4t e to the power of 3t plus 5 cosine 2t. Okay. Very complicated, huh? There's 3 terms here. Okay. So you look at, first you look at f of t. There are 3 terms. So you deal with each one of the terms separately. So for t squared, so let's y of t. So first for t squared. And for t squared, that is basically the second row at here, right? It falls into this one. So you go to the second column because it's order 2. So you should take it as at squared plus bt plus c. So this is basically like a YP1 corresponding to t squared. Then next, so you look at this 4t e to the power of 3t. Okay. So this is actually a combination of t and e to the power of 3t. Right? So there are 2 terms multiplying together at here. So in this case, for t, you use the second rule. So if it's a t, then it's k1t plus k0, right? So for t, you're going to use that. Make sure you choose different, and you make sure you choose different constants. You'll use ABC already. So now I'm using D and E. So this is for t. Okay. And then e to the power of 3t, right? E to the power of 3t here is supposed to be a constant times e to the power of 3t. Okay. So, I mean, you could choose a constant like this. However, now because you look at this, because you already got constant d and e at here, right? So you don't really need an f anymore because once you multiply the f into that bracket, it's just to become another constant. So that's why you just have to multiply by a e to the power 3t here. So that's the second one, right? Look at this. The second one here, you can call it YP2. And the last one is a sinusoidal function. So you go to your table, sinusoidal, which falls into here. So that's your choice. Like it, choose a different constant f cosine 2t plus g sine 2t. So that'll be a yp3. Good? Yeah. If you can simplify, then you can go ahead and simplify, but usually you don't need to. Okay. So if you have a question like this, it's probably going to take an hour to solve at least. Right? It's going to take a lot of time. A rule of thumb to solve this kind of thing is, right? You should solve it. You don't put everything there to solve. You should solve it like you solve 3 different questions. One question is the homogeneity equal to solve equal to t squared. Another one you equal to this. Another one equal to this. Okay. So then you solve the constants basically 3 times separately. Okay. Instead of you mixing everything, you could, but it will make your expression like a gigantically long expression. Okay. It's going to be very confusing. So basically, that's the 3 rules. Yes. Yeah. Could it be negative? That's a good question. That's a really good question. I haven't really thought about that. Yeah, let me think about it. That's a really good question. Yeah. I had to look into it. Yeah. Good. Any other tricky questions? Okay, that's it for today. Okay, so now let's look at some concrete examples. Okay, how do I think we can finish one example. It's y double prime 4y equal to at squared. Okay. Try this one here. Second order differential equation with f of t equal to at squared. Okay, step 1 is to get the YH. To get the YH, you follow the procedures. Okay, homogeneous function. Construct the characteristic equation. So lambda squared plus 4 equal to 0. You get 2 solutions which are complex conjugate roots, so positive and negative J2, which means alpha is 0 and beta is 2. Right? So your real part is 0, imaginary part is positive and negative 2, but we call the 2 as beta. So according to the solutions for the complex conjugate roots, you get C1 cosine 2t plus C2 sine 2t. That's your general solution for the homogeneous one. And then step 2 is to find the YP. So YP depends on the form of the input function f of t, which is at squared. So now I look at the table, follow the basic rule. My choice for YP would be, okay, let's use K2 t squared, K1 t plus K naught. Right. According to the table, this is your choice of YP. So now I need to find what is K naught, K1, and K2. So the next step is to do this. So how do I find each one of the coefficients? Here's a step what you can do. Maybe I should actually, for the formality, you check a multiplication rule. Okay, so modification, you compare your choice YP with your YH. Apparently, they don't duplicate at all, right? So I don't need to apply the modification rule. So now I go to solve for the three constants at here. So what do? First, you calculate the derivative. So we're going to use substitution. We're going to substitute YP back into the second order non-homogeneous equation. Because always remember, YP is supposed to be a particular solution, right? Yeah. So YP prime equal to 2K2T plus K1. YP double prime is equal to 2K2. Then we sub YP prime and YP double prime into this Ly equal to AT squared. Back into this non-homogeneous one. So this time, this is the step you have to be careful, okay? So Y prime, let's do that. So Y prime is 2K2 and plus 4Y, so plus 4 times K2T squared, 4 times K1T, 4 times K0 equal to AT squared. Okay. So then group similar terms. Okay, group similar terms. Then what do we have? We don't have too much to group, but this is your highest order term. This is your second highest order, first order term, and then you got two constant terms equal to AT squared. Okay, so next step is K. So once you're over here, then there's a technique. Okay, so look, you have a left equal to the right, and the left and the right, they are both polynomial, right? So this is a polynomial and this is a polynomial, and they're both polynomial the same order. Highest order is 2. Highest order is 2. So then the next step is called compare coefficients of both sides. Both sides. When you want one polynomial to be the same as the other polynomial, which they are of the same order, then the coefficients of the two polynomial needs to be exactly the same. So which means the coefficients for t squared needs to be the same. The coefficients for the t needs to be the same. So what will be the coefficient for the t here? 0. And the constant, same thing, should also be 0. So now you got 3 equations, 3 variables. You will be able to solve for all 3 numbers. Because K1 is 0, K2 is 2, and then K0 equal to -1. Okay. So finally, your YP is equal to 2t squared minus 1. Okay, so your general solution is y equal to YP plus C1, Y1 plus C2, Y2. Right? Construct it as 0. Okay, so we'll look at a few more examples, okay, different scenarios for this second order non-homogeneous one in the next lecture. Okay, and that'll be after reading break. So have a good break, but maybe do some catch up if you can. Okay. Thank you. Bye.